Hey there, in this video we're talking about data hiding and specification separation in C++ object-oriented programming. And this is basically sections 13.4 to 13.6 in the Gaddis textbook. Now, in the last video, we finally started object-oriented programming for the first time. So part of what we're dealing with in this video here is a little bit more detail about what's the difference between the private versus the public sections of a class, and really why is that there. But the overall theme for today's video is how do you separate out work on a big team? Remember, professional programs can be hundreds of thousands of lines long. They can have a dozen or 20 or 50 programmers working on it. So what are some techniques with object-oriented programming to parse out the work to different members of a big team like that? That's really important. Okay, so let's talk about that. Let's talk about object reusability. So we are assuming that the objects, the classes that we create, are going to be reused by other programmers. And possibly many other programmers, possibly not just one or two people, but a dozen or 10 or maybe 100 around the world. So there could be many other programmers using the classes that we make, and they might all be working on one really big program together. They might be working in a bunch of different programs, reusing the classes that we make. And therefore, the objects that we make, the classes that we make, should be as convenient as possible and as flexible as possible for others to use. You know, let's like the string class, okay? String objects, right? We all use strings. Every single program we ever make probably uses a C++ string object all the time. So I'm personally really glad that the people that made the string class set it up in such an easy, flexible to use way that we can all start using strings very easily in all the programs in C++ that everybody makes around the world, frankly. Now here's an example of that. So there's a person that's probably going to have the responsibility for making a class the first time. So in my example here at the top of the picture, maybe that's Alice. She's the class programmer. And let's say that Alice has created a class to handle mathematical matrices, right? A grid of numbers. And Alice's class is really well set up and it knows how to add matrices and multiply matrices and compute the dot product and the cross product and find the determinant and all kinds of great stuff like that, okay? So that class, that matrix class, is probably going to get used, and maybe you've got a bunch of application programmers together working on like one big program that uses matrices, and maybe this is Bob and Kathy and Dennis all working on one team. Or, you know, maybe they're working on completely separate programs. So maybe Bob is working on telephone networking that needs to use matrices to track the connections in a network. And maybe Kathy is doing 3D graphics that uses matrices pretty heavily. And maybe Kathy here is doing artificial intelligence game strategy, possibly. I guess that's Dennis, right? So you could be using the matrix class in a whole lot of different programs, in a whole lot of different contexts, and the way that Bob wants to use it versus how Kathy wants to use it versus Dennis could be very different, and we want to give as much flexibility and as many different features for how you access a matrix object as possible. So as we go forward, keep in mind the idea of a big team, right? So normally you don't just write one class, use it yourself, and then throw it away, right? You're going to be using it communally on a big team, and you want everybody to find it easy to use, not hard to learn, not hard to memorize the parts they need to use. Okay, so what are the pieces in C++ that support that? Okay, well that's this difference between private and public parts is one part of this. And this is called encapsulation or data hiding. You've got the private interface in a class, and the basic idea is the private part, that's the parts of an object that are accessible only to the class programmer, maybe only Alice, right? So that scopes out a particular part of the class that only the class programmer is allowed to touch, only they can access it. This is all enforced by the compiler. If someone else tries to break that rule, the compiler will not permit it. But the great thing is that the application programmers don't have to think about it. They don't have to memorize it. They don't have to learn about it. It just doesn't matter to them because they can't access the private stuff in the first place. So why bother? But on the other hand, the public interface, that's the parts of an object that are accessible to everybody, accessible to the application programmers. That's the stuff that they expect to use in their day-to-day work. I mean, obviously, Alice, the class programmer, she can also access that stuff. So the public interface is the part that everybody does need to learn and memorize because everybody can use that. So this private versus public part very clearly marks which parts you need to worry about. And that's huge. Okay, that's the basic idea, right? And there's a whole lot of different languages that use those ideas in possibly different ways. Here's the details of specifically what that looks like in C++. So as we saw before, there's this private label in the class that marks the stuff that can only be accessed inside the class, inside the member functions of the class. And we saw that last time, like with the width and the length member of the rectangle class, we could access width inside one of the member functions inside the class. When we tried to access it over in the main function outside the class, the compiler did not permit that. Okay, that's exactly what's happening. Now remember, we make all of our data, all of our variables private usually. The public label, that marks the part of the class that can be accessed anywhere in any code base. Could be from, you can access that stuff from within the object, you can access it from outside the object, like in the main function, or like from another class. You can access the public stuff anywhere. It's all in scope anywhere that you've included the class definition. And that's exactly what we saw last time. Now, the little reveal on this slide, obviously, is there is a third access type in C++ that's actually called protected. And we really don't need to worry about that right now, but to make a long story short, that's stuff that can be accessed inside the class, just like with private, and you can also access it from inside any child class. So when we get up to chapter 15, we'll see that you can make one class, and then you can like evolve it. You can create classes based on that are called child classes or derived classes. And if something is marked as protected in the parent, you can also access those members in the child classes. And we'll see why you want to do that up in chapter 15, but don't worry about that for now. Don't forget that we usually make our member data, the variables, we make it private. Usually we make the functions public. And that's how that goes. We'll see exceptions. All right, so let's reflect on why we have private member data. Why do we do this data hiding of put the data in the private part so that application programmers cannot directly access? Again, that's called encapsulation or data hiding. And that right there might be the single biggest, most important feature about object-oriented programming that has made it possible to construct big programs with big teams. Prior to that, part of that little tidbit of the data hiding, it was so much harder to get that stuff to work. So we should definitely really thoroughly understand this and reflect on this here. So we kind of clued you into that before. I've said it a couple times. The private section establishes parts of an object that will be handled automatically. The class programmer, Alice, needs to know about that. Everybody else can ignore it because the private member data will be managed internally and you don't need to worry about it as an application programmer. So again, application programmers don't need to know about or manipulate those parts with the private data. They just don't need to know about it. And at this point in the course, like usually, second semester programming, I might have one or two students that make the comment in class of like, do I have to memorize all this stuff? There's so much stuff. And I mean, you're not wrong. We've said that computer science is probably the most complicated thing that human beings have ever done. So it's not like they're wrong about that. But here, finally, we have this private section of a class that specifically marks off this stuff. If you're an application programmer, you do not need to memorize this stuff. You don't need to know about it. You don't need to learn it because you're literally not even allowed to access it. So when you are working on a big team, how great is that? How great is that to actually have a part that's specifically, explicitly marked off as something that you don't need to learn? Considering all the stuff we do have to deal with, that's a huge benefit. In addition, on the same theme, making data members private protects other programmers from accidentally corrupting the internal processes of an object. So Alice has her matrix class set up, and it's adding and it's multiplying, it's doing all this complicated stuff that matrices do. And, if Bob is working on a particular day and he gets a little fuzzy or he didn't get enough sleep or something like that, it would be very easy to accidentally overwrite one of those member variables. We've all done that before, accidentally overwrite a variable when we shouldn't. Well, by marking it private, that's just off the table. The compiler won't permit that. If Bob tries to access one of those parts of the object, it just cannot happen because the compiler won't let that program be compiled, actually. And you'll get a very clear error. We saw that in our example in the last video, actually, of it says this particular member data is private here. You're not allowed to access it. I will not permit it. So that will help, both Alice, that she's not having her class get screwed up, and also Bob, that he's not making a bad mistake on a particular day. So that's a great, great security feature on a big team. And fourth bullet point here, by accessing data only through the public member functions, right? Whenever you want to change the data, you have to go through a public function. The objects can do input validation internally. They can do error checking. They can log what's happening to a data file, like keep a record of all the changes that are happening in a data file. They can normalize the data to some kind of format that's important. And all that's going to happen automatically, and the application programmers don't have to worry about it. It's going to be happening automatically inside the functions, and it's going to look like all that stuff is just happening automatically by magic, right? The logging file is happening, and the data file on the hard drive, that's happening. The input validation is happening automatically. How great is that? So more stuff that we've been spending time on in the past doing manually, maybe that's just going to become automatic for us because it's inside the object. Wonderful. So all kinds of great stuff about having private member data managed only inside the class and not scattershot through 100,000 lines of programming code that everybody needs to memorize and learn about. Super. Again, that right there, single most important thing about object-oriented programming, and it has made it possible to make huge, complicated programs that were largely not possible before. So that is just gigantic. So that having been said, here's a couple types of member functions. You're going to be doing, the application programmers are going to be doing all their work through these public functions. So here's a couple types of public functions that you should be familiar with, because they're going to be in every single class you ever deal with. So you should look at this and become very, very familiar with this. Two different types here. Type number one are called accessors, right, or getters. So they're functions that are, that have a name of get something. And so the idea here is, here's a function that just retrieves a value from a private member variable without changing it. So here's how application programmers learn about the values that are inside the object. And what you'll have here is you'll have a function that has a return value. It's the same type as the member data. So if I have a piece of member data in my rectangle class called width, and it's a double, then my getter will also have a return type that's double, because the whole point is it's going to be returning that width number. And I'm going to call it get whatever the variable is. So I'll call it get width, or I'll call it get length, or whatever it is that you're dealing with. The parentheses will be empty because getters usually don't take any arguments. You don't need to pass any information in. The object has already recorded what the width is, right? You don't have to tell it at this point. So the only thing that function has to do is just dig it up in the member data and just return it. So as you can see here, our accessors are going to have a return type the same as the member. There will not be any parameters. There should not be any I/O in that function. There's no sin or count or file handling or anything like that. There should be no side effects. It should not change the variable. It should not change any other variables, right? And as we saw before, like with the get width function, all it does is just return width. That's it, okay? And probably most of the time, any piece of member data that you have, you'll probably have a getter that gets that particular piece of member data for when the application programmers need to find out about it. Okay, very, very common. Most of our member data will have that. Maybe not all the time, but most of the time. And the second thing that's very common is what's called a mutator. So a mutator or a setter, and we usually call these set whatever the name of the variable is. The point is that's a member function that will store a value in a private member variable or changes its value somehow. So mutate, right, means something that's changing. So these are the functions that will be changing the contents of your object. changing the contents of the member variables inside your object. And what we usually do with our mutators is, see, they're going to have a void return type. They don't need to return anything because the whole point is you're sending in information to the object. So it doesn't have to return anything back, it's just receiving information. So these will always be a void return type. They will have one single parameter, the same as the member type. So back in our rectangle class, we had a function called setLength, and length is a double. So the setLength function has to take in a double because for the number that's going to get saved in the length. And again, whatever the variable is, I had setLength, I had setWidth, right? Probably one per member variable, probably. So you'll have one single parameter. The type is the same as the member type. Again, there will be no IO in one of these functions, definitely no sin, definitely no count. It's not printing anything, right? It's just setting one of the member variables. That's the point of a setter. And again, no side effects. Don't change other variables. Don't print stuff to the screen, right? Don't open a file. Just save the data that's coming into the function, save it in the appropriate member variable. That's all this does. Okay, so very, very simple functions. These are usually just one line each. You can look back at the rectangle class, or we'll see it in a couple slides again, and see how very short they are, but you should be familiar with the format of the accessors and the mutators. Accessors, they're just going to return one piece of member data. Mutators, they're just going to take one piece of member data and save it, right? No printing, no sins, no IO, nothing else, just those jobs. Okay, now previously when we were defining the code for our functions to implement them, normally what we're doing is we had the prototypes in the class definition, and then we're actually implementing the code after that, after the prototypes in that class declaration. But this slide is pointing out there is a second option called inlining your member functions. So you actually are allowed to provide the code for a class member function in the same line where you gave the prototype inside the class declaration. So, that might possibly shorten your code maybe. I wouldn't want to do this a lot. Inline functions are only appropriate, I would say, for very short function bodies when the function is only 1 or 2 lines at most. Ideally, we've been saying all along that you really want a function to fit on screen at one time. When another programmer reads your function, right, they ought to see start and end and see the whole thing visually on the page in sight at one time. Ideally, same thing for class declarations. Class headers, right, ideally they're only long enough that they fit on screen at one time and you can see the whole thing in one single view. So if you start inlining really, really long functions, that your class declaration is going to get too long to fit on screen at one time. So I would not want to do that. But if your function is only 1 line long or 2 lines long, maybe at most, then maybe you can just put them in the class declaration and it doesn't get too long like that. Here's an example here of a getWidth function. Now hopefully you're going to recognize that as an accessor. It's a getter. Not going to take any arguments, not too surprising about that. Presumably the width of this object, I guess it's not the same as our rectangle class. The width here must be of type int, I guess, in this particular class. Getters, accessors, they don't have any side effects. They don't change any member data. So actually, you should probably tag them all with const would be the ideal thing. Right? These aren't going to change anything about the class. And so this is a really good example. Getters and setters, right? They're usually 1 line. The getters usually just return 1 member variable, and the setters just set 1. So actually, the accessors and the mutators actually are a good example of something you could probably inline, save a little bit of time there, and why not? If it's 1 line, okay. But don't go any further than that. There's a longer story to the story of inline functions, and if you look at this section in the book, there's possibly a trade-off between speed on the CPU and space in your memory system. So it's possible that an inline function is going to save time on the CPU when you call it, but take up more space in memory in your executable. So there's a little bit of a trade-off there. and the compiler gets to make some decisions about that trade-off. But in addition to just putting the code in a different place, you actually are telling the compiler you're requesting it to not really do a function call, but just repeat the code in different places. And then maybe, again, hopefully your program will run a little bit faster, but be a little bit bigger. And that might be a trade-off you might consider. Again, there's a deeper story to that. Read that section of the book. For our class, you don't have to worry about it. I'm not going to expect one way or the other. So for our class, that's a detail we don't need to concern about. But read that section of the book if you want to see the extra story about that. All right, so here's an example of that. Here is a revision of our rectangle class, now with a few inline member functions just for the getters, because we know they're just one line long. So we'll look at some other details about this on the next slide, actually. But the important thing here is now, instead of having the code implemented after the class header, you do have it inline in the same line in the actual class definition. So here's get width that just returns the width. And here's get length that just returns the length. And here's get area that does that job that we saw in the last video. Okay, so this class definition will still fit on one screen in our IDE. We can see the whole thing from start to finish. That's not too bad. That's fine. That's fine. It saves us the lines that we needed to actually implement it later on. So, that's an option. That's good. Okay, now, here's the other thing we wanted to talk about today. Again, theme for today, separating work out on a big team. So our programs are going to start to get bigger. And maybe our teams are going to start to get bigger with more people. But certainly our programs are going to start to get bigger. So what we want to start doing, like you do with larger programs, is when things get big, the answer is always split it up into separate parts and just deal with one part at a time. So here we're going to want to start to split the specification, which is to say the class definition, from the code implementation and put them in separate files. Put them in separate files on the hard drive. That's going to be very smart and very common. Okay, so what you're going to see here is we're going to start splitting our programs up into at least 3 files now. And what we usually do in C++ programming is that the class declarations declaring the class are placed in what's called a header file, conventionally called classname.h. So for example, if I'm working with my rectangle class, I'm probably going to put the definition of the class, right, the private data and what the public functions are, in a file called rectangle.h. That's not a .cpp file, that's a .h file for header file. And that's what we usually do for our class definitions. So another question is, well, where does the code go? Well, the member function definitions, the actual implemented code, are put in what's called a source code file, which is going to be classname.cpp. For example, for my rectangle class, I would actually put the code in a file called rectangle.cpp. The things that actually do the setters and things like that. Now, for the compiler to know about the member data that you're using in those functions, you're going to have to pound include the header file. So the top of rectangle.cpp, among other things, it's going to have to pound include rectangle.h so that the compiler can copy in the definitions of the class. What is the member data? What are the prototypes for the functions, right? So you're going to be including now a file that you actually made for a header file, which is actually what all that does. It just copies in these definitions from another place. Now that's just the class, right? Where's the application, right? That's just stuff that Alice, the class programmer, is probably going to be making. But now Bob, Kathy, and Dennis come in with their application, and that's going to be in yet another file. So the application programmers that use the class are going to be a third file, like what was Bob working on? Telephone networks. Okay, so maybe Bob has a file called telephonenetworks.cpp, and if he's using the rectangle class, he's going to have to, again, pound include rectangle.h because that's where the definition of the rectangle class was. A lot of advantages to this. I mean, number one, right, you don't need to copy paste the class definition. Back in chapter 12, we had this example of an address book application where we had this address structure, and we had one program that did reading and one program that did writing, and we had to copy the structure definition identically in those two programs. And if we'd slightly changed one, then the combination wouldn't work. So this would be actually a much better idea, is you could put that struct, or we'll be putting the class definition in just one header file, and then just pound include it. And once again, you're not repeating yourself. And that's the primary philosophical point about computer science, is you shouldn't ever repeat the same code. Here, you just put it in the header file and then include it. So much better. And another advantage, now these three files you can parse out among three programmers. So you can come in, decide on what the design is for a program, and Alice, you go work on rectangle.h, Bob, you go work on rectangle.cpp, and Kathy, you go work on telephone networks.cpp, if that's what the job is today. So now you actually do have separate files, and now it actually is legitimate for the first time to give those out to separate workers and then put them together at the end of the day. So finally, and this is what professional programs just look like all the time. So I'm so glad we finally see this. Now, let's just talk about how you have to organize that. It's going to be a little bit different in any IDE. For our class, we are using Dev C++. So let's just talk about what that's going to look like there. In Dev C++, you're going to have, for a multi-file program, like probably about everything we do from now on, you have to organize that in what's called a project. And my students have certainly seen me. I'm in the habit, anytime I start a new program, I always make a new project in Dev C++. And then it gives me at least like a starter template source file that I get started with all the time. But if you haven't been doing that on your own already, you're going to have to do that with multi-file projects. And what you'll do is you'll open up Dev C++, and the very first thing you'll do is click on File, New, Project, Console Application is what we're doing all the time. Give a good name to the project, save the project file. That's a .dev file that it makes at that point. Now that's the same thing that I've been doing all the time anytime I make a new project, so that's not too different. But the new thing is, let's say you're using some example from the book that's got a header file and an implementation file and an application file, right? So now you're going to click on Project, Add to Project, and select those 1, 2, 3 files or however many there are, right? And now the project has a record that these are all the files that are part of this project. Now, if you're adding to it, like if you're adding to an object-oriented programming and you need to make a brand new class, this is kind of nifty. You can click on File, New Class, and Dev C++ actually automatically makes both the .h file and the .cpp file at one time. And it actually kind of starts filling it out for you. And then you just have to fill in all the details of what's my member data, what's my functions, what's the code. So that's kind of nice. It's that one click actually makes 2 files for you set up properly, and then you start adding the details. So that's pretty neat. Anyway, so once you have that stuff all together, then you hit the compile button like normal. It's going to compile all those files. It's going to link them all together into one executable. And of course, you have to test your program as usual. Now, let's think about all the stuff that's happening there when you hit the compile button. Right? There's a lot of details there that we've been kind of hand-waving all along that now you're going to see those details in front of you maybe for the first time. Here is an illustration of the process of compiling probably in an IDE. And once again, this is actually a picture from Gaddis, the Gaddis textbook, chapter 1. So we knew that this was going to happen. We knew this is going to happen when we're going to start doing bigger programs in an object-oriented context. So we get to look back at chapter 1 again now that it's really important, is we're working on some source code files. Right now, not just one of them. I've got a .h file, I've got an implementation CPP file, I have an application CPP file, got a whole bunch of source code written in C++. You hit the compile button. Now, the first thing that happens is there's what's called a preprocessor that comes directly from the C language. It's technically called the C preprocessor. And basically what that does is it reads all those pound lines. It reads the pound includes, which are including other files, possibly header files. You know, IOStream is actually just a CPP file somewhere on in your computer. We could actually go look up what it was. And the preprocessor goes, finds those files and actually copies them into memory inside your source code. You don't see it because it's in memory, but it actually does modify your source code at that moment to copy paste all the definitions from all of those header files. That's actually what the pound includes do. There are some other pound directives to the preprocessor that we're going to start seeing now. There's not just pound include, but there's pound if and pound define and pound if def and a bunch of other stuff actually. So those are all commands to the preprocessor that modifies your source code in memory. Okay, then the actual C++ compiler comes through and it's going to translate that high-level modified source code and translate that to the object code, one file at a time. And then technically what it does is it translates that to the object code that the CPU actually knows about. And it's going to create, for us now, it's going to start creating a separate .o file to contain the object code produced from each separate source code file. So if I have rectangle.cpp, the compiler translates that, and it's going to print out rectangle.o. And if I have telephone networks.cpp, the compiler will translate that and print out telephone networks.o for the object code that's actually the result of the compiler. Right? That's what it says over here. Object code files will now start appearing in our project folder as these .o files, and there'll be a whole bunch of them. And then a third thing happens, and then there's a thing called the linker that comes through, takes all those separate .o files, those separate object files, and links them together, glues them together, matches the memory addresses, syncs them up properly, and actually the result of that is now an executable file on Windows. Right? Then you actually have your .exe file. So you're going to start to see a whole bunch of files running around because we've got a header file, a source code file, an application file, possibly more of those. I got a project DEV file, probably a make file. I have 1, 2, 3 object files, and then finally I have an executable file. So I'm probably going to have at least 9 or 10 files running around for all of our projects starting today. Let's think about another, one more advantage before I get off this slide, or actually, test this, is another advantage to having separate source code files and separate .o files is when the programs get really, really large, you're going to have like 1,000 source code files maybe. And the compiling is going to take a long time. So it's actually pretty common on big programs that you hit the compile button and you just go and you get lunch because it's going to take an hour. It's going to take 2 or 3 hours. It's going to take a long time if you compile the whole program with all of the files. But let's say that you had previously, like yesterday, you compiled your program and you have the 1,000 .o files, okay? And all you've just done is you've just modified one of the classes. You've only modified telephone networks.cpp and all the other stuff hasn't been changed. Well, you can still reuse all of those .o files, and all the compiler has to do is just compile your one single file, write out that .o file, and then the linker glues it together with all the pre-existing .o files, and now that takes 30 seconds. So if you had all of your code in one giant file, you're going to be sitting there for 3 hours. But if you have it separated out and you have pre-compiled .o files, it's a snap. Save you all kinds of time, and you're going to be much more efficient as a programmer. So all kinds of advantages, again, to taking something big and splitting it up into separate sections. Okay, so when we're working with new classes, we should expect to test our classes. Again, we're going to kind of have the hat on of the class programmer, kind of like Alice, right? Before I release my matrix class to other programmers, right? I want to confirm that my class works the way it should, and it's flexible, and it's easy to use, and it manages the data properly, right? Before I hand it off to Bob and Kathy and Dennis, I want to confirm that it's actually going to work like we expect for them. So for any class we create, we should expect to make a test driver program. It's not an application that really does any useful job in the world. It's just testing our class before we give it to other programmers. So what we would probably do in that test driver program is we'd instantiate one of our objects, of course, confirm we can do that, test one of the mutators, test one of the setters in the object, check the state, right? Make sure that that was recorded properly with one of the accessors. So maybe make a rectangle, set the width of the rectangle, print out the width with getWidth to confirm that the width that we wanted was actually recorded, okay? And repeat that for all the different public functions. And of course, don't just write out numbers on the screen. Use clear labels to indicate what's being tested so other people can run the test driver and confirm that the class is working according to the specification. So we're going to start to get in that habit going forward pretty routinely. We'll have a class and our labs quite frequently will turn into, let's write a test driver for this class and confirm that we know how to use it and that the class is actually working as we would expect. And we'll make an object and I'll call some mutator functions and we'll print out the results of some accessor functions, confirm the results are correct, and then go on to the next class. Okay, you might know as a little side point, if you're looking at the code that comes for labs with the Gaddis textbook, it ends at chapter 13. It actually ends in the chapter that we're currently dealing with. And we have a lot more work to do with object-oriented programming, a lot more stuff to learn. But probably what we're going to be doing in our labs going forward is take a class from the book and write a test driver. That actually is going to become a lot of our labs, so kind of look forward to that in the future. And that's probably that's actually what you do in the professional workplace to confirm that your class is well structured, and that's probably what we should start doing for practice ourselves. For example, that's what we're going to do in the next lab with my students. So when we get together in person, we're going to look at, what we're going to do is we're going to go into chapter 13, and there's a folder for rectangle version 2. And it's got a header file and it's got an implementation file. It does not have an application file yet. So what we'll do is we'll practice in Dev C++ making a new project, adding the header file and the implementation file, right? Look at particularly the header file, see what's available, and we're going to write a test driver for that class and confirm that we can make a rectangle object, we can call the setters, we can call the getters, it records the information properly. Maybe we'll try that once or twice or even 3 times to get some practice at that. So I think that's a good piece of practice and a good habit to get into, because that's what we should do when we make a new class, and that's what a lot of our labs are going to look like going forward. So I think that's a pretty good point. So great, more stuff about object-oriented programming to come in the future. Next time, we're going to look at the issue of constructors and destructors. Constructors set up an object automatically without the application programmer doing any work at all, and destructors clean up an object automatically without the application programmer doing any work at all. So every class that I've ever worked on has constructors and destructors, and they make life, again, the class programmer is probably going to set up, and they make life so easy for Bob, Kathy, and Dennis, the application programmers, because the objects just automatically initialize themselves automatically, clean themselves up out of memory automatically. So handy to have there. Makes it so much easier to use your objects as an application programmer. So we should definitely learn about that. And I'll see you next time for that.